The Ku band is the 12 to 18 GHz portion of the electromagnetic spectrum in the microwave range of frequencies. This symbol refers to K and the, in other words, the band directly below the K band. In radar applications, it ranges from 12 to 18 GHz according to the formal definition of radar frequency band nomenclature in IEEE Standard 521-2002. Ku band is primarily used for satellite communications, most notably for fixed and broadcast services, and for specific applications such as NASA's Tracking Data Relay satellite used for both Space Shuttle and International Space Station communications. Ku band satellites are also used for backhauls and particularly for satellite from remote locations back to a television network's studio for editing and broadcasting. The band is split into multiple segments that vary by geographical region by the International Telecommunication Union. NBC was the first television network to uplink a majority of its affiliate feeds via Ku band in 1983. Some frequencies in this radio band are used for vehicle speed detection by law enforcement, especially in Europe. Segments and regions. The Americas. Segments in most of North and South America are represented by ITU Region 2 from 11.7 to 12.2 GHz, 10.750 to 11.250 GHz, allocated to the FSS. Uplink from 14.0 to 14.5 GHz. There are more than 22 FSS Ku band satellites orbiting over North America, each carrying 12 to 48 transponders, 20 to 120 watts per transponder, and requiring a 0.8-m to 1.5-m antenna for clear reception. The 12.2 to 12.7 GHz segment is allocated to the BSS. BSS normally carries 16 to 32 transponders of 27 MHz bandwidth running at 100 to 240 watts of power, allowing the use of receiver antennas as small as 18 inches. Europe and Africa. Segments in those regions are represented by ITU Region 1 and they are the 11.45 to 11.7 and 12.5 to 12.75 GHz bands are allocated to the FSS. In Europe, Ku band is used from 10.7 to 12.75 GHz for direct broadcast satellite services such as those carried by the Astra satellites. The 11.7 to 12.5 GHz segment is allocated to the BSS. Australia. Australia is part of ITU Region 3 and the Australian regulatory environment provides a class license that covers downlinking from 11.70 GHz to 12.75 GHz and uplinking from 14.0 GHz to 14.5 GHz. Indonesia. The ITU has categorized Indonesia as Region P, countries with very high rain precipitation. This statement has made many people unsure about using Ku band in Indonesia. If frequencies higher than 10 GHz are used in a heavy rain area, a decrease in communication availability results. This problem can be solved by using an appropriate link budget when designing the wireless communication link. Higher power can overcome the loss to rain fade. Measurements of rain attenuation in Indonesia have been done for satellite communication links in Padang, Cibinong, Surabaya and Bandung. The DAR model for rain attenuation prediction is valid for Indonesia. In addition to the ITU model, the DAR model has become an ITU recommendation since 2001. This model can create a 99.7% available link so that Ku band can be applied in Indonesia. The use of the Ku band for satellite communications in tropical regions like Indonesia is becoming more frequent. Several satellites above Indonesia have Ku-band transponders, and even Ka-band transponders. Newskis, launched in December 2002 and positioned at 95 degrees east, contains only Ku-band transponders with a footprint on Indonesia. The IP-Star satellite, launched in 2004, also uses Ku-band footprints. Other satellites that provides Ku-band covers Indonesia are Palapa-D, MEAS-83 3/8, JS-80 Corporation, JCS-84B, AsiaSat-5 Sint-2, China's R-11, Korea Telecom, Korea's R-8, ABS-2. Other ITU allocations have been made within the Ku-band to the Fixed Service, Radio Astronomy Service, Space Research Service, Mobile Service, Mobile Satellite Service, Radio Location Service, Amateur Radio Service, and Radio Navigation. However, not all of these services are actually operating in this band, and others are only minor uses. Advantages. Compared with C-band, Ku-band is not similarly restricted in power to avoid interference with terrestrial microwave systems, and the power of its uplinks and downlinks can be increased. This higher power also translates into smaller receiving dishes and points out a generalization between a satellite's transmission and a dish's size. As the power increases, the dish's size can decrease. This is because the purpose of the dish element of the antenna is to collect the incident waves over an area and focus them all onto the antenna's actual receiving element, mounted in front of the dish. If the waves are more intense, fewer of them need to be collected to achieve the same intensity at the receiving element. Also, as frequencies increase, parabolic reflectors become more efficient at focusing them. The focusing is equivalent given the size of the reflector is the same with respect to the wavelength. At 12 GHz, a 1-meter dish is capable of focusing on one satellite while sufficiently rejecting the signal from another satellite only 2 degrees away. This is important because satellites in FSS service are only 2 degrees apart. At 4 GHz, a 3-meter dish is required to achieve this narrow of a focus beam. Note the inverse linear correlation between dish size and frequency. For Ku satellites in DBS service, dishes much smaller than 1 meter can be used because those satellites are spaced 9 degrees apart. As power levels on both C and Ku band satellites have increased over the years, dish beam width has become much more critical than gain. The Ku band also offers a user more flexibility. A smaller dish size and a Ku band system's freedom from terrestrial operations simplifies finding a suitable dish site. For the end users, Ku band is generally cheaper and enables smaller antennas. Ku band is also less vulnerable to rain fade than the Ka band frequency spectrum. The satellite operator's Earth station antenna does require more accurate position control when operating at Ku band due to its much narrower focus beam compared to C band for a dish of a given size. Position feedback accuracies are higher and the antenna may require a closed-loop control system to maintain position under wind loading of the dish surface. Disadvantages. There are, however, some disadvantages of Ku band system, especially at frequencies higher than 10 GHz in heavy rainfall areas. A noticeable degradation occurs due to the problems caused by and proportional to the amount of rainfall. This problem can be mitigated, however, by deploying an appropriate link budget strategy when designing the satellite network, and allocating a higher power consumption to compensate rain fade loss. The Ku-band is not only used for television transmission, which some sources imply, but also very much for digital data transmission via satellites, and for voice audio transmissions. The higher frequency spectrum of the Ku-band is particularly susceptible to signal degradation, considerably more so than C-band satellite frequency spectrum. A similar phenomenon, called snow fade, can also occur during winter precipitation. Also, the Ku-band satellites typically require considerably more power to transmit than the C-band satellites. Under both rain fade and snow fade conditions, Ka and Ku-band losses can be marginally reduced using superhydrophobic lotus effect coatings. Moreover, snow fade is caused not only by snow accumulation on the antenna, but also by attenuation caused by airborne snow along the RF signal path.